Okay, so I wanted to start by saying thank you to the Time in the Valleys Museum for inviting me to be a part of the incredible webinar series that they're hosting. And like Donna said, the museum offers amazing virtual programs on local Catskill history. And if you haven't already, be sure to check out their event calendar on their website for more upcoming programs. I'd also like to thank two geologists, Danny Davis and Chuck Verstraeten, whose expertise and guidance were extremely helpful for this presentation. So my name is Haley Springston. I'm the Watershed Planning Coordinator with the Rondout-Neversink Stream Program. And the Rondout-Neversink Stream Program is a project of Sullivan County Soil and Water Conservation District. We work in partnership with the towns of Denning and Neversink, and we're funded by the New York City Department of Environmental Protection. Our office is located just down the road from the Time in the Valleys Museum in Grahamsville, and we offer a wide range of environmental restoration services, grant funding opportunities, and educational content to the community located within the Rondout and Neversink watersheds. We offer ongoing educational events and stream-related programming, so you can follow us on Facebook or Instagram at Rondout-Neversink, or join our mailing list by emailing info@rondout-neversink.org to stay updated on our latest events. So today I'll be talking to you all about the geologic history of Catskill streams, and I'll be leading us on a virtual hike along a Catskill stream to give you a better sense on how to read the geologic history from the rocks around your part of the Catskills. A lot of people, when they hear the word history, they often think of past human events. And oftentimes when we think of history as studying the stories and events of people, countries, civilizations. Basically, we think of human history. Today, I'll be focusing on geologic history. So human history seems like a really long period of time, but in comparison to geologic history, or the history of the Earth, human history is rather short. So this diagram is the geologic time scale, and geologists use it as a timeline with the formation of the Earth, which occurred about 4.6 billion years ago, all the way to the left at the start of the timeline, and all the way to the right, we have present day at the end of the timeline. And here's another example of the geologic timescale. In this picture, this timescale is oriented vertically instead of horizontally. And you can see here that geologists break up the timeline into segments of time, also called eras. And you can see the eras here, Paleozoic, Mesozoic, Cenozoic, for example. And then they take the eras and break them up into even smaller sections of time known as periods. You might be familiar with the Jurassic period, for instance. But today we're going to be taking a closer look at the Devonian period, which occurred between 420 to about 360 million years ago. And you can see it on the diagram here between the Silurian and the Mississippian. And I think this particular diagram is a really great way of visualizing the time scale because it illustrates a very basic but very important principle of geology, which is that older rock layers are generally positioned below younger rock layers. And geologists refer to this as the principle of superposition. And we'll go back to this idea later on in the video today. And thinking in terms of millions or billions of years can be hard to do. Sometimes it's hard to wrap our mind around that concept of time. But if you break down the entire history of the Earth into one day, like you see in the diagram here, humans show up on the scene at about 11:59 p.m. and the Catskills are formed at about 9:30 p.m. And back to the geologic timescale, you can see here that the Catskill Mountains begin to form in the Devonian period about 380 million years ago. So the Catskills are much, much older than human history. The Catskills have undergone countless changes in the landscape, and the rock that you see in the Catskills today serve as historical artifacts that preserve those changes. So when you walk alongside a Catskill stream, know that there are bedrock and pebbles that are over 300 million years old. So you can literally run your hand along the banks of Catskill streams and touch rock that has existed longer than the entirety of human history. And I want everyone to keep that in mind the next time they go for a Catskill hike with friends, or the next time they drive past a Catskill waterfall. And what's amazing to me as a geologist is that through science and research, it's possible to examine the rocks we see every day and determine how the landscape has changed over time. And you can use rock to read the history of the surrounding landscape. And that's what I'll be showing you guys today. So in my opinion, the best way to learn about geology is to get outside and just start looking at rocks. And earlier this year, I had scheduled a Stream Geology walk and talk event, but with COVID, we decided to change the event into an educational video. So back in June, I created and shared a video that allows viewers to have a similar experience as a geology hike. And today I'll play clips from the video for you all, and in between the clips, I'll review what we've seen, and then I'll review how Catskill geologic history still plays a huge role in our everyday lives. Just keep in mind that with the size of this Zoom call, the quality of the video clips will be lower than usual. But if you do want to see the high quality video, you can view the full video on YouTube on the Rondout-Neversink Stream Program YouTube channel, or by searching Reading Catskill Streams, Catskill Stream Geology on YouTube. So before starting any hike, it's important to follow leave no trace principles. So whenever you go for a hike, you want to make sure that you carry out all the materials that you carried in, and you don't want to leave any evidence that you were ever on the trail. And that'll be easy for us today since we'll be virtually hiking along the stream. So here is a video clip. This is the Catskill stream that we'll be walking along today. It has gorgeous sections of stream banks that make it easy to appreciate its geology. And this beautiful stream is located in the Neversink Reservoir watershed. And if you're unfamiliar with that term, a watershed is also known as a catchment or a drainage basin, and it's the total land area that drains to a specific location. So the waters of this Catskill stream eventually flow into the river, and the Neversink River eventually flows into the Neversink Reservoir, which you can see circled in this diagram here. The waters of the Neversink Reservoir are transported downstate and are eventually used as water supply for New York City. So the stream water we see today in these video clips will eventually have made its way to the New York City water supply. When we walk alongside a Catskill stream like this one, and we take a look at the smooth, rippling stone that lines the channel, it's easy to wonder how the Catskill landscape was formed. You can ask questions like, how did this stream get here? Did this landscape always look like this? And how did the Catskill landscape form? So this is how the Catskill region looks today. It's located west of the Hudson River in New York State, and the Catskill Park landscape spans over 700,000 acres. And today, the Catskill landscape has moderate elevation peaks. The highest peak, Slide Mountain, has an elevation of 4,190 feet, which you can see. I've marked the location of Slide Mountain on the mountain, or on the map with the yellow mark. However, This Catskill region used to look drastically different than it does today. The Catskills used to feature an ancient, massive mountain range that some geologists think the peaks were as high as the Himalayan mountain range. So how is this possible? And for reference, circled is the Neversink Reservoir, pictured in the map there. So how did the Catskill landscape form? Well, about 380 million years ago, during the Devonian period, the world looked like this. Throughout the geologic timescale, the continents have changed shape and moved around the globe. And the area that came to be the Catskill region was located here, with where the yellow marker is on this map. During the Devonian period, the Catskill region was much closer to the equator than it is today. Here's another rendering that isn't quite as accurate, but can help us visualize where the Catskill region was located about 380 million years ago. The staggering ancient mountains of the Catskills began to form about this time in the Devonian period. So during the Devonian period, an ancient landform collided with what is now the eastern coast of North America. And this collision is an extremely powerful and extremely long process. And the collision takes about 50 million years start to finish, which is a very long time. And you can think about this continental collision sort of as the hood of the car smashing into a wall during a car crash. So during a car crash, parts of the hood are going to buckle outwards. And this is similar as the ancient landmass. When it collides with North America, the ground is sort of scrunched together and the ground is pushed upwards. And this event forms an incredibly massive mountain range along the American coastline known as the Acadian Mountains. And geologists call this process of mountain building an orogeny. So this is a cross-sectional diagram that shows a side view of what happened during the Acadian orogeny. So along the western edge of the coastal Acadian Mountains, there was an existing shallow sea that begins to deepen. And you can see on the map below, the light blue area shows an approximate area of the western shallow sea. So looking at the diagram above, you can see that the rising mountain belt begins to erode, shedding mud, sand, and gravel, which is deposited along the western slope of the mountain range, where the slope meets the shallow sea. And that process of shedding sediment is indicated by the brown dotted arrow in the upper diagram. And you can see on the map below, the yellow marker again indicates where the Catskill landscape once was. And the red area indicates this section where the Acadian mountain range meets the western shallow sea. So this is a closer look at that boundary that was marked in red on the previous map. And this is the boundary between the Acadian mountain range and the western shallow sea. So in the diagram along the left, this area over here along the left represents the shallow sea. And then you can look and see this curved line that cuts across the diagram. And that sort of represents the shoreline or the beach that formed where this shallow sea meets the Acadian mountains. So atop the freshly risen Acadian mountains, rivers and streams form and begin flowing downslope towards the western shallow sea. And these Devonian rivers and streams erode or wear down the peaks of the Acadian mountains. And the rivers and streams, as they erode the material, they transport it and they deposit it or drop the material along the river channels and nearby floodplains. And as the rivers continue to flow down the slope into the very slow moving shallow sea. They deposit their remaining material, forming river deltas. And over time, this process of deposition along the river channels, along the floodplains, and along the deltas creates a layer of sediment over a mile thick known as the Catskill Delta Complex. And you can see the Delta Complex circled in red on the map here. And the Catskill Delta Complex is over a mile thick, and it's made of the material that were shed from the peaks of the Acadian Mountains that were eroded and transported by rivers. So here is a video clip. Today, you can see the remains of the Catskill Delta Complex. So the solid, unbroken rock we see along this Catskill stream is the remains of the Catskill Delta Complex. Present-day Catskill rivers and streams continue to erode, transport, and deposit the remains of the Catskill Delta Complex. And this means that the loose sediment we see carried by Catskill streams today, so the pebbles, the gravel, and the sands that you pick up from Catskill stream beds are largely composed of the same sediments that were once carried by the ancient Devonian rivers over 300 million years ago, which I think is pretty amazing. So here's another video clip, and it's an example of a bedrock controlled stream channel. So I'm gonna go ahead and play that for you guys.
Bedrock is solid or liquefied rock. Where I'm standing is an example of a bedrock controlled channel. In this section of the stream, the riverbed is made primarily of exposed visible bedrock.
So to sum up that video clip, basically what you're looking at in this video section is an example of a bedrock controlled stream channel. And bedrock, like we said, is solid or lithified rock. And here's another video clip that gives an example of what sediment is. So sediment is loose material that is broken off of solid bedrock through weathering and erosion. And sediment that's transported by flowing rivers or streams is called alluvium. So the pebbles and gravel and sand along Catskill streams, the fancy word for them is alluvium.
This is an example of an alluvial channel. An alluvial channel is made of loose, unconsolidated material that makes it easy for the river to change its shape during high flow events.
So our stream that we're walking along, this section is again an example of an alluvial stream channel. Now I want to take a closer look at two common rock types found in Catskill streams. And this is a video example of sandstone. And sandstone is a sedimentary rock, and it's primarily made of sand-sized particles that have been cemented together. And it's common to find quartz minerals within Catskill sandstones. And quartz is highly resistant to weathering processes at the Earth's surface. And sandstone is easy to be identified by its gritty texture and its visible sediment grains. Another common rock type is mud rocks, and they're easily found throughout the Catskills. This is a video clip of shale, the rock that I'm holding. And you're probably familiar with shale. It's pretty easy to recognize because it easily breaks into thin, platy slabs. And you can see the thin layers, less than a centimeter thick. And these thin layers are known as laminations. And shale is considered part of the rock class known as mud rocks. Mud rocks are fine-grained sedimentary rocks. They're mostly made of very small fine-grained particles, less than 0.063 millimeters in diameter. This section of bedrock is made of two types of mud rocks, mudstone and shale. So you can see the unlayered mudstone shelf here and transitioning to the thin layered shale located above. And the mud rock class includes shale, mudstones, and siltstones. So this sandstone bedrock formed from the compacted sediment the Devonian streams transported from the peaks of the Acadian Mountains nearly 380 million years ago. And the sandstones that we see are remnants of the ancient river channels that formed the Catskill Delta complex. So I want to take a closer look at the sedimentary structure in the sandstone here. And you can see the dipping layers in the sandstone represented by, I drew some red arrows above them. And these dips are where the river dropped the sediment it was carrying. Here's a helpful diagram that sort of explains this process. So when the sediment piles up in a river channel, the flowing water pushes against it and it slides down the pile, forming a sloped layer that you can see in the second picture of this diagram. And the layers dip toward the direction of flow. So by reading this rock section, you can sort of read its depositional history. And this area used to be the bottom of a riverbed, and the ancient river, you can tell from the dipping layers, flowed in this case from left to right. You can also see a harsh line right above the dipping layers that separate two sloped layers. I drew in a dashed line there. And the harsh lines between the sloped crossbed layers are erosional surfaces, and it shows where the river deposits were eroded, and it indicates a shift in the channel direction. And this pattern is known as crossbedding, and crossbedding can be found in sandstones throughout Catskill River valleys. And these repeated crossbedding structures are evidence that the rock you see was formed as the ancient river channels shifted and meandered over time. And so the next time you go on a hike and you see crossbedding structures, you'll be able to read the flow direction of an ancient river. So the mud rocks that we've seen on our virtual hike today formed within the floodplains of the ancient Devonian River Channel network. So a floodplain is an area of low-lying land located alongside the edge of a river channel that becomes flooded during high flow events. So if you take a look at the diagram, during a high flow event, the water level will rise, and eventually the water will overtop these natural levees and spill over into the floodplains on either side. And once they spill over, the waters immediately slow down and they begin to drop or deposit the sediment that they were carrying. So you can see here in the cross-sectional view of the diagram how layers of sediment are deposited across the floodplain. And Catskill mud rocks can have some really interesting fossils and features in them. Red mudstones are often highly fractured in a hexagonal pattern that you can see here on the picture on the left. So you can see that this cracked feature throughout the red rocks, and this cracked feature forms as the floodplain floods and then dries out repeatedly. So the fine sediment gets soaked and then it dries out over and over again, causing the fine-grained material to crack and harden into this pattern that we see today, which is pretty interesting. And then the picture on the right is an example of a trace fossil. So if you look closely at mud rocks along the stream, you can see green patterns like in the picture here that show impressions of the roots of ancient Devonian primitive trees and small plants that were growing alongside the floodplain. And in some other gray sandy siltstones, you can sometimes find the impressions of broken branches that covered the bottom of pools or ponds after a high flow event. So what do the mudrock and sandstone bedrock layers tell us about the area's geologic history? If you walk along the stream, you'll notice there's a repeated pattern of sandstone and mudrock layers overtopping each other. So this is evidence that the location used to feature meandering streams. So as the ancient channels meandered or moved from left to right, they wove across the landscape. And so a single location would change from being an active stream bed to a stream bank to a floodplain area. And what's really cool about Catskill rivers is that you can actually use them to travel through time. And so the sedimentary bedrock layers of the Catskills have remained, for the most part, geologically undisturbed. So if you look at this diagram, we can imagine it as a Catskill hill. So according to one of the founding principles of geology, the principle of superposition, which we talked about earlier today, younger rock layers sit above older rock layers. For instance, the lowest rock layer in a sequence is the oldest. The rock layer deposited next is younger than the first rock layer and sits above the first layer. So looking at this diagram, you can imagine that you are the figure and you're going on a Catskill hike. And let's say on the other side of the hill, there's a Catskill stream and it's flowing down from the peak all the way down. And as you finish your hike, you're walking along the stream and you're walking in the stream channel. And as you walk downstream, you're actually walking towards a lower elevation and you're moving lower in the sequence of sedimentary bedrock layers. So that means that as you're walking downstream, you're actually walking along older and older rock layers. So when you walk downstream and you're walking with the flow of a Catskill stream, you're actually traveling backwards in geologic time. And when you walk against the flow of a Catskill stream, you're ultimately traveling forward in geologic time. So that virtual hike gives us a basic understanding of how the Catskill landscape we see today was formed. But how does the geologic history of the area we live in affect our everyday life? So even though these geologic events took place over thousands or even over millions of years ago, they still play a major role in almost every aspect of our life. So topography, for instance, or the shape of the land that we see has been carved by the structure of our bedrock and by the areas, the Catskill area's past periods of glacial activity. And so, for example, the slope or the steepness of the Catskill mountain trails that we hike along today is due to our geology. The natural resources available to us and the soil health and agriculture of the Catskill area has been determined by geology as well. And I'll be focusing on how present-day Catskill stream behavior and water quality is affected by our geology. So the geologic history of the Catskill region, including its original deposition as the Catskill Delta Complex, along with its historic periods of glacial activity, has determined our present-day stream behavior and water quality. And I will give bonus points to whoever recognizes the location of the upper right photo. So Catskill bedrock geology determines our land's resistance to erosion. The mineral composition of bedrock strata determines how well the landscape can hold up against the processes of erosion, along with other factors. The Rondout-Neversink watersheds have a history of glaciation, and from approximately 1.2 million years ago to around 11,000 years ago, glaciers carved out the river valleys that we see today. So our geologic history has a significant effect on the behavior and the characteristics of today's streams. The steepness or the slope of the channel is affected by the underlying geology's resistance to erosion, and the cross-sectional shape, or how wide or narrow or deep or shallow a stream is affected by the shape of its river valley. So when you have narrow valleys and steep mountain walls, such as Rosgan Stream Type A, you have the river will behave much differently than if it were located in a wide, flat river valley, such as Rosgan Stream Type D. So streams with narrow valley walls surrounded by steep mountains have a higher tendency for flash flooding occurrences. So our geology also has a major impact on our water quality today. For the Catskills, turbidity is a major concern for water quality, and turbidity is defined as the measurement of relative clarity of a liquid. But basically, turbidity is how cloudy or murky a liquid is. So the photo in the top right shows a stream that is temporarily experiencing high turbidity following a rainstorm. And I'll give ultimate bonus points if you can recognize any of these photo locations within the Rondout-Neversink watersheds. So turbidity has negative impacts on water quality. It leads to poor aquatic life habitat conditions. It deters healthy fish populations, and turbidity also decreases drinking water quality. So water with high turbidity levels can be unsafe to drink. Turbidity can be caused by algae imbalances or other organic contributors, but in the Catskill region, a major contributor to turbidity is fine-grained sediment. And during the period of glaciation within the Catskills, layers of fine-grained clay and silt sediment were deposited by glaciers moving across the landscape. And when these exposed layers of fine-grained glacial sediment erode into Catskill streams and rivers, the small particles take a long time to settle, they cloud the water, and this increases the turbidity. The Rondout-Neversink Stream Program works to prevent harmful erosion along our local streams, protecting our local streams from the negative impacts of turbidity. Turbidity as it relates to the stream program. Rondout-Neversink Stream Program is dedicated to improving water quality of the Catskill streams, which includes measures to improve water clarity, but also extends beyond turbidity to offer additional improvements to water quality and ecological health for the local watershed community. So the Rondout-Neversink Stream Program offers stream feature inventories where we identify those fine-grained sediment exposures that are often higher contributors to turbidity. We also offer channel restoration design, and we do landowner streamside plantings, which is offered through the Catskill Stream Buffers Initiative. This targets areas that are likely to have imbalanced erosional activities. We also provide grant funding for local improvements to infrastructure, and that's given to those who follow our stream management plan recommendations. We also target biological stream health, flood hazard mitigation, research funding, and we also provide educational content and training. So again, it's a wide effort, and if you have any questions or want to know if you're eligible for a streamside planting, just send us an email at info@rondout-neversink.org, or you can also visit our website at rondout-neversink.org to learn more about what we have to offer.